Okay, in summary, what can we say? First of all, we know that a capacitor is just a pair of plates separated by the insulator called a dielectric. The equation that gives us the capacitance of a capacitor is Q equals CV. We know that when you put some charge onto the plates, you get a repelling potential across them. As a result of that, the more charge you have on it, the more potential you have across it, and therefore the more potential you need to put into it or put across it to get more charge on it. Therefore, the energy in a capacitor is given by the equation E equals half QV. So we can substitute this in a few times and we can get E equals a half Q squared over C and a half CV squared. That's all good. We also know that when we're discharging a capacitor, we can say, well, either the current or the voltage or the charge is all given by I naught or EV naught, whatever it is, times by E to the minus T over RC. Now, the I naught, V naught or Q naught is the total charge at the start, the initial charge or current or voltage or whatever it was, the starting value, okay? The full value, if you were, okay? The R and the C is the resistance of the circuit, and the C is the capacitance of the circuit. And so RC is we call that the time constant. Time constant. Okay, so when the amount of time, when you have the same number of seconds as the when the time that's elapsed since you started discharging or charging it is equal to, in seconds, is equal to the resistance times by the capacitance of the capacitor, we have T over RC is equal to 1, and when T over RC is equal to 1, or rather sort of minus 1, then E to the minus 1 is 0.37. Okay, so that means when the total value, the current value, is 0.37 times the initial value, you are at the time constant. That will be RC, and this will be 0.37 of the full, if that's 1. On the flip side of that, if you're charging it up, you give the opposite value here, and of course what that means, if the total final full value for charge or voltage or current or whatever it is going to be 1, then the RC, this value here for RC will be, when this is 0.63% of the final. Now that as soon as I've looked at this, I've realised this is a load of pants, because the current doesn't go up, the current only goes down. There you go. So V will go up to the full value and Q will go up to the full value. Of course the current won't do that at all. That's only going to apply in this situation because it's discharging. Right. I think that's it. The last thing to say is, I haven't mentioned this anywhere through it, but of course we know that in theory, because let's just think about discharging cycle, as this gets less and less and less, there's less potential difference, so it's driving less charge and less current off, so it should theoretically never get to zero. Similarly, it should never ever actually truly fully charge. But if you put in 5 times RC, or make this basically put E to the 5 in your calculator, what you find is that you get way less than 1% left over there, and way more than 99% when it's in this situation. So we say that 5 times RC is the time constant, is the time to be totally charged or totally discharged. Right, that's capacitors. Basically, that's the theory. That's all the theory of capacitors that you need to know for AQA. Next up, we'll look at some problems.